assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So this problem begins by giving us the equation that A gas forms 2B gas and several different Kc values, and wants us to find the partial pressures of A and B at these different Kc values. And so the first several steps of all of these, A, B, and C, are going to be the same. And so I'll just start with the first few steps. And so the first thing we're going to do is do an ICE table, ICE, and we're told that that's initial change equilibrium. We're told that A starts at 0 atmospheres and B starts at 1 atmosphere. We're going to add x here and subtract 2x here based on their values before the A and the B. And so at equilibrium here we have x, and at equilibrium here we have 1 minus 2x. And so we can then set up the equation Kp equals the partial pressure of B squared over the partial pressure of A. And those are our equilibrium pressures right here. So we can set that equal to 1 minus 2x squared over x. Now, we're also going to need, so this, everything up to this point will be the same for A, B, and C. However, our value for Kp is going to change. And so how we're going to determine that is I'll go to a new page. So for letter A, we're given a Kc value of 1. And so Kp is equal to Kc times RT to the delta N, which is the change in number of moles from products minus reactants. And so our Kc is 1. We're told to make any assumptions that we need to make, so we're assuming that R value 0.082057 and 298 Kelvin, and then the delta N is 2 minus 1 or 1. And so when we do this, we get 24.45. And so if we plug that into our Kp equation that we had on the previous page, we will get 24.45 is equal to 1 minus 2x squared over x. And so the first thing we want to do is rearrange this to a quadratic, and so I'll go to a new page to do that. When we rearrange this to a quadratic, we end up with 4x squared minus 28.45x plus 1 equals 0. And now that we have it in a quadratic, we can use the quadratic formula to solve for x. And we get several values for x, 2 values for x, but the only one that makes sense is 0.035, and that's because the other value is too large and will give a negative partial pressure, which is not possible. And so now that we have this x, we know that our partial pressure of A equals x, so it's just 0.035 atmospheres. And our partial pressure of B is equal to 1 minus 2 times x, which gives us that the partial pressure of B is 0.93 atmospheres. And so these are our final answers for part A. Now if we move over to part B, everything we did on the first page is still the same. That ICE table and everything is still accurate. We're just going to get a new value for x because we have a new Kp. And so we'll use our same equation for Kp. So Kp equals Kc times RT delta N. And the only thing that's changed here is our Kc. And so we end up with the Kc that is given is 1 times 10 to the minus 4th. And then before our RT to the delta N was equal to 24.45. And so this just gives us 0.002445. And so now we can do the same thing with the Kp. Kp still equals 1 minus 2x squared over x, but this time that whole thing equals 0.002445. And so again, now we want to rearrange this to a quadratic, and I'll go to a new page for this. And when we rearrange this to a quadratic, we end up with 4x squared minus 4.002445x plus 1 equals 0. And now I kept all these significant figures here just so that the calculation will be more accurate. And so this gives two pretty reasonable x values, 0.518 or 0.483. And now the problem, and the reason we know it's not this one, is because if we plug this into our value for partial pressure of B, 1 minus 2x, that will give a negative value for the partial pressure. And we know that the partial pressure can't be negative, so we know that this has to be our proper x. So now for part B, the partial pressure of A is equal to our x, 0.483 atmosphere. And the partial pressure for B is equal to 1 minus 2 times x for 0.483, which is equal to 0.034 atmospheres. And so these are our final answers for the partial pressures of A and B in this problem for part B. Now for part C, again, we have the same ice table, same everything, same Kp equals Kc times RT to the delta N. However, this time our Kc is 1 times 10 to the 5th. So we multiply that by our 24.45, and we get that our new Kp is 2.45 times 10 to the 6th. And so when we plug that into our Kp equation, 2.45 times 10 to the 6th equals 1 minus 2x squared over x. We rearrange this to form a quadratic, and I'll go to a new page for that. And we end up with 4x squared minus 2.45 times 10 to the 6th x plus 1 equals 0. And so now when we solve for x, the only value that makes sense is 4.1 times 10 to the negative 7th. And so our partial pressure of A is 4.1 times 10 to the negative 7th. And our partial pressure for B is 1 minus 2 times 4.1 times 10 to the negative 7th. And so that essentially just ends up being 1.0 atmospheres. It's actually 0 point and then about like 10 nines. And so we just round that to 1.0 atmospheres. So there's our partial pressure for B, and our partial pressure for A is this. And this makes sense since on the previous page our Kp was very, very high, which means it heavily favors the products, and therefore the partial pressure of A is essentially 0, and the partial pressure of B is essentially 1 atmosphere. But that is the final answer for this problem.